Next section, message passing systems. Message passing provides a mechanism to allow processes to communicate and to synchronize their actions without sharing the same address space. It is particularly useful in a distributed environment, where the communicating processes may reside on different computers connected by a network. For example, an internet chat program could be designed so that chat participants communicate with one another by exchanging messages. A message passing facility provides at least two operations. Actually, they are system call. The first is send, message size fixed or variable. The second is receive message. Message sent by a process can be either fixed or variable in size. If only fixed-sized messages can be sent, the system-level implementation is straightforward. This restriction, however, makes the task of programming more difficult. Conversely, variable-sized messages require a more complex system-level implementation, but the programming task becomes simple. This is a common kind of trade-off seen throughout operating system design. If process P and Q want to communicate, they must send messages to and receive messages from each other. A communication link must exist between them. This link can be implemented in a variety of ways. We are concerned here not with the link's physical implementation, that means such as shared memory, hardware bus, or network, but rather with its logical implementation. We have direct or indirect communication and synchronous or asynchronous communication, automatic or explicit buffering. So we look at issues related to each of these features next. First, naming. Processes that want to communicate must have a way to reach to each other. They can use either direct or indirect communication. And the direct communication, each process that wants to communicate must explicitly name the recipient or sender of the communication. In this scheme, the send-receive primitives are defined as send P message, send a message to process P, receive Q message, receive a message from process Q. A communication link in this scheme has the following properties. A link is established automatically between every pair of processes that want to communicate. The processes need to know only each other's identity to communicate. A link is associated with exactly two processes. Between each pair of processes, there exists exactly one link. The scheme exhibits symmetry in addressing, that is, both the sender process and the receiver process must name the other to communicate. A variant of this scheme employs a symmetry in addressing. Here, only the sender names the recipient, the recipient is not required to name the sender. In this scheme, the send and receive primitives are defined as follows. Send P message. Send a message to process P. Receive ID message. Receive a message from any process. The variable ID is set to the name of the process with which communication has taken place. The disadvantage of direct communication is that changing the name of a process must examine all other process definitions. All references to the old name must be modified to the new name. With indirect communication, the messages are sent to and received from mailboxes or pods. A mailbox can be viewed abstractly as an object into which messages can be placed by processes and from which messages can be removed. Each mailbox has a unique identification. For example, POSIX message queues use an integer value to identify a mailbox. The send and receive primitives are defined as follows. Send a message. Send a message to mailbox A. Receive a message. Receive a message from mailbox A. So, in this scheme, a communication link has the following properties. A link is established between a pair of processes only if both members of the pair have a shared mailbox. A link may be associated with more than two processes. Between each pair of communicating processes, a number of different links may exist, with each link corresponding to one mailbox. Now, suppose that processes P1, P2, and P3 all share mailbox A. Process P1 sends a message to A, while both P2 and P3 execute or receive from A. Which process will receive the message sent by P1? The answer depends on which of the following methods we choose. Allow a link to be associated with two processes at most. Allow at most one process at a time to execute a receive operation. Allow the system to select arbitrarily which process will receive the messages. The system may define an algorithm for selecting which process will receive the message. A mailbox may be owned either by a process or by the operating system. If the mailbox is owned by a process, that is, the mailbox is part of the address space of the process, then we distinguish between the owner, which can only receive messages through this box, and the user, which can only send messages to the mailbox. Since each mailbox has a unique owner, there can be no confusion about which process should receive a message sent to this mailbox. When a process that owns a mailbox terminates, the mailbox disappears. Any process that subsequently sends a message to this mailbox must be notified that the mailbox no longer exists. In contrast, a mailbox that is owned by the operating system has an existence of its own. It is independent and is not attached to any particular process. The operating system then must provide a mechanism that allows the process to do the following. Create a new mailbox. Send and receive messages through the mailbox. Delete a mailbox. Synchronization. Communication between processes takes place through calls to send and receive primitives. There are different design options for implementing each primitive. Message passing may be either blocking or non-blocking, also known as synchronous and asynchronous. Blocking end. Blocking send. The sending process is blocked until the message is received by the receiving process or by the mailbox. Non-blocking send.